Hello friends, in this lecture we will discuss on this analysis of flanged section. So please open your code page number 96 of IS 456. Now before going to the codal provision, let us discuss what is the meaning of this flanged section. So you think of a hall. Okay, so this is a hall. In this hall you have walls and beams. Okay, both these are the beams given on this hall. So I am not going only 3 4, there may be many more beams. Okay, so these are the beams, these are the end beams and these are the intermediate beams. So you can see in your classroom also, you look top, above your head, you can find the number of beams. Now, if you cut a section in this beam, what will happen? You cut a section in your okay, you will take section XX. So if you take the section, it will look like this. If you cut, it will look like this. So there's a beam here. It will go like this. There's a beam here. Go like this way. Okay. So this will look like section. Now this portion is the slab portion and this is the beam portion. And these behavior of these kind of beams, that this when the beams are integrally built with this slab, that means monolithic construction. If you cast your concrete, you put the reinforcements in beam and slab and then cast it at a time, or they call it monolithic construction. So in that case, the beam behaves with a part of this slab. So this beam will behave like a T beam. Okay, this will look like a T, so this will behave like a T beam, and the end beams will behave like a L beam. So this is the T beam and L beam. So the behavior like T beam and L beam. Now this is called the flange of this T beam, and this is called this wave, width of this T beam or the L beam, width of wave, and this is called the thickness of flange. So that is nothing, the thickness of slab. Thickness of slab is equal to thickness of flange. And how to calculate the width of flange, we'll see in the later classes. Or there is a special code provision how to find the width of the flange. And now this is the depth of wave. This is the depth of wave. This is the depth of flange. So this becomes the total depth of the beam. So the beam is a T beam or L beam. So these sections are called the flange section because they have a flange. Now what happens here? Now above the neutral axis, what you see, if you take neutral axis here or maybe here, the area in compression increases. So the moment of resistance of T section is more than the moment of resistance of similar rectangular section, because the area in compression planes is more. They will contribute more moment of resistance to the section. Now see what kind of things may happen now here. Now you will find either this neutral axis. There are 3 parts. One is your wave, other is your planes. So neutral axis may lie in your planes or it may lie in your wave. So you go to your code G2 plane section. First is XU less than DF. If your neutral axis is within the planes, then the moment of resistance may be calculated from equation G1.1. What is G1.1? That is just like a rectangular section. You see here, G1.1 is section without compression reinforcement, a rectangular section. So you just calculate this section as a rectangular section, G1.1. But the width B will be considered as BF. All these formulas of these 3 cases is valid here for the plane section when XU is less than BF. If your neutral axis lies in planes, then the behavior of this beam will just like a rectangular section, and you use this all the formulas to calculate this limiting moment of resistance, under reinforced moment of resistance, and to calculate neutral axis. But only thing, the B value width will be equal to the width of the planes. That's the first part. So for XU less than DF, moment of resistance is equal to maybe taken as a rectangular section. Now, if XU is greater than DF, what will happen? So there will be two cases: how to find the limiting moment of resistance, or how to find out the under reinforced sections. So the first case is limiting value. What it says, the limiting value of moment of resistance, that is the limiting or balance section of the section, may be obtained by the following equation if df by d does not exceed 2. So there are two cases: df by d does not exceed 2 means less than 0.2, or df by d is greater than 0.2. So there are two conditions. For these two conditions, you can find the mu limiting. The formula is given here. Okay. So what a formula given? 0.36 xu maximum by d minus 1.42 xu maximum by d fck bw square. The same formula for this is given here. Only b is taken as bw. So that means if you divide this T section into two parts, so this is a T section. Okay. So one I will tell, this is the entire section as a rectangular section. Okay, this is the rectangular section. So it can equivalent to a rectangular section of BW into D. Okay, and then plus this part. So this part, what is the value? This is BF. Okay, and this is your BW. So this will be equivalent to a section having the width is equal to BF minus BW and the depth is equal to DF. So what is the moment of resistance of this? Now it is given 0.45 FCK is the stress in concrete, BF minus BW is your width, DF is the depth. So stress into area is the force into moment of into lever arm. But the lever arm, so the CG will be here, DF by 2 from top up, and the CG of the reinforcement is D from the top. So the difference is D minus DF by 2. So how? This is the formula derived for this case. So with this, if DF does not exceed 0.2, then you have to use this formula. Okay. Now if it exceeds 0.2, then you come to here. Whenever this ratio exceeds 0.2, okay, whenever this ratio exceeds 0.2, the moment of resistance will be calculated like this. The same thing, 0.36 xu maximum by d, 1 minus 0.2 xu maximum by d, fck bw square, plus again here 0.45 fck is the stress. Okay, 0.45 fck stress, bw minus bf minus bw is the width, but here it is taken yf instead of your xu maximum, it is taken yf. What is yf? Yf into d minus yf by 2. Yf is given a value 0.15 xu plus 0.65 df, but not greater than df. So you calculate the value of xu. So yf is y1 is equal to yf is equal to 0.15 xu plus 0.65 df. Df is nothing, thickness of the planes, and xu is the your lever arm. So calculate the value of whether it is xu maximum. If it is xu maximum, put your xu maximum because you have taken xu maximum here. So for limiting case, xu is equal to xu maximum. So this is the two formulae how to calculate the value of the moment of resistance T section. So T section is divided in two parts. One is the rectangular section, just like a rectangular section you are calculating, plus another compression part where it is the width is equal to BF minus BW, depth is equal to DF. So for these two parts combined, you will find the moment of resistance. Now what is G2.3? If XU maximum greater than XU greater than DF, what the meaning? XU, that means XU maximum is greater than XU greater than DF. That means XU is greater than DF means it lies in the planes, and XU maximum greater than XU means XU is less than XU maximum. So neutral axis lies between the limiting neutral axis and the depth of planes. So then moment of resistance may be calculated equation G2.2 when df by xu does not exceed 0.43. So now here comes two cases: df by xu is less than 0.43, doesn't exceed less than 0.43. Another is df by xu exceeds 0.43. Okay. So in both cases, what you will do? In first case, you have to use the G2.2 as the previous formula, and G 2.21 when it exceeds 0.43. Only substitute XU maximum by XU. So in both the formulas, what will do? Suppose a df by XU exceeds 0.43, then you have to use this formula, and here in place of XU maximum, you put simple XU. Okay, wherever there is a XU maximum, put the value of XU and calculate the moment of resistance. Similarly, so first was limiting. This is basically for the under reinforced sections. So again, if you go for the under reinforced sections, for the first case, you have to replace this XU maximum by XU, and you can calculate this value of MU. So when df by XU less than 0.43 and df by XU less than 0.43. So based on that, you can calculate the moment of resistance of the sections. Now let us see some example problems on the when neutral axis lies in the planes. So when neutral lies in planes, you will see some problems. Neutral lies in planes. So the first case, you have to assume whether neutral axis is in planes or neutral axis in wave. That you would first confirm. Then the problem will be tackled. So if it is lies in planes, then it will look like a rectangular section. Formulas of all rectangular section will be applicable. If it lies in wave, then we have to come for this G 2.2 and 2.1. Now, in the first problem, a T-beam section, all the data is given, width of the planes is given, 100, thickness of planes is 120, effective depth is given. The AST, 4 numbers 25 means AST is equal to pi by 4 in 25 square into 4. FCK is 20, FY 415, calculate ultimate moment of resistance. So write down all the data. So first is you have to find out, as we have discussed, first find out XU by D. Okay. So if you lies, you assume, you don't know whether it is in planes or in wave. So first assume neutral axis lies in planes. So if it is in planes, then you have to first use the formula for the rectangular axis. XU by D is equal to 0.87 FYST by 0.36 FCK BF. You see here, it is not small b, it is BF. You have to take BF. Now XU comes out to be 65.5, and your plane's thickness is given 120. That means XU is less than DF. So your assumption is correct, and XU is also less than XU maximum. So neutral axis lies in planes, and it is a under reinforced section. What the moment of resistance? Put the formula for this. Rectangular section, and then in case of B, put the value of BF. The same formula 0.87 FIST D into 1 minus FIST by FC. Here you find it is only BF. So in case of B, you have to put BF and put all the values to find the moment of resistance doing the calculations. Now in the second problem, we see the limiting. Find the limiting. It will say the limiting moment of resistance. T-beam section, all the data is given. Thickness of planes, effective depth. Calculate the limiting moment of resistance. Limiting moment of resistance means neutral axis lies in planes. So if you want to find out this ultimate moment of resistance or limiting moment of resistance, you have to put the formula for the single reinforced section, and only in case of B is equal to put BF. Okay, everything remaining same, we'll put that and find the value. It's just like a rectangular section. Neutral axis lies in planes. Here is not written, but you should write this neutral axis lies in planes. Okay, neutral axis lies in planes. It will give you in the question, or you have to confirm that neutral lies in planes. It's not flying, not in wave. If neutral axis lies in planes, then only you can find MU limiting is equal to just like a rectangular section. So be confirmed, or if it is not given in the question, then the some step has been not taken, like the previous problem. Find out the value of XU and check XU is less than DF. Then find the value of MU limiting. So either the question will give in that neutral axis lies in planes, or you have to calculate yourself and then find the limiting moment of resistance. Now the third type of question again will come to find the area of steel. Okay. Now the moment is given, working moment is given here. So working moment is given means you have to find the ultimate moment by multiplying 1.5. So ultimate moment is given, BW is given, effective depth D is given, thickness of flange is given, and width flange. So all data is given, only unknown is area of steel. Okay, area of steel you have to find out from this data. So let us first find out where this neutral axis lies. Now come to the problem. So all the data is given, AST unknown. So now what will be? Assume XU is equal to DF. So if XU is equal to DF, what is the capacity of this section as a rectangular section? So the capacity of section as a flange section will be ME1, that is equal to 0.36 FCK BF. Okay, XU into D minus 0.42 XU, and put XU is equal to DF. So if the neutral axis is just at the level of this your DF, this is your DF. Okay, so if neutral axis is here, this is your DF. So neutral axis lies here at this level. So this is the DF. What is the capacity of the section? So put XU is equal to DF. The capacity comes out to 218. Okay, but what is the moment is given for design? 150. That means the capacity of this section is more than 150, means the neutral axis must lie here in the planes. Then only the capacity will be less than this value. If it will cross this value, the value of the moment is more than like 230, 240, then the neutral axis lies in wave, not in this. So you by knowing the capacity of this section, you can also decide whether neutral axis is in planes or neutral axis is in wave, when this moment capacity is given and the area of steel is not given. Now what is the capacity of the under reinforced section? So calculate the value of AST. The formula already we have used in many cases. Moment is given, find of area of steel, and the area of steel, only thing, the same formula you are going to use, but we have to take this B is taken as BF here. Okay, only thing is you have to take B is equal to BF. That value you have to find out. AST is equal to this, so the formula will come same, but find B is equal to BF. 0.5 VF D FCK by FY, 1 minus square root of 1 minus 4.6 mu by this. So this area is comes out to be 908.93 millimeter square. So these are three kind of problems which you will find when neutral axis lies in planes. So either you have to find the neutral axis, or you have to find out the area of steel, or sometimes you have to find the moment resistance as a balance section. So with this we conclude this session for this plane section. In another class we'll discuss this analysis of plane section or this single reinforced sections with your neutral axis lies in wave, and another class will discuss the double reinforced plane sections. So with this we conclude this class, and have a nice